I guess the first question is, why build your own SDR? There's a pretty saturated market out there at the moment, and you can get quite good hardware for a pretty affordable price. Really, I just sort of wanted to learn a bit about the magic of RF design. Having a useful system at the end of it is sort of a bit more of a bonus. Other than to learn more, there is still a question of why go to all the effort. Ideally, the project should bring something to the table that doesn't really exist outside otherwise. Because you could just take 4 of these and pair them up and it would be the same thing. What's different about the board that's been built as part of this project is that they all share a single clock source, and all of the sampling is all done in sync across the 4 channels. Now this means that you can do things which you can't otherwise do. By being synchronized to a single clock, you can actually measure differences in phase between the different channels, and so you can measure difference in the time of arrival between what's coming into each of the channels. So that means that you can do direction finding. Another application which looked quite interesting, there's also a thing called passive radar, which involves looking at a signal that's reflected off a target. It would be like sort of a broadcast signal because you're not transmitting anything out, and comparing it against the actual source. So you'd have one antenna pointed, say, at a TV station, and then another antenna pointed at a target, and you look at the phase difference of the reflected signal versus the original reference signal. So these are all things that you really need multiple channels to be able to do, and those channels have to be synchronized. Now, in the initial stages, I knew I wanted to do an SDR, but I wasn't too sure about what functionality and features to have. Now, I wanted it to have more than the famous RTL SDR dongles which you can get. That was sort of a given. It probably wouldn't feel like a very fulfilling project if it was completely just recreating something that already existed. So I thought perhaps I'd add transmit functionality. Now, in the end, didn't end up doing that. It's just a bit too technically challenging and some concerns about the legality of it as well. Now, for the most part, the SDR that's been designed for this project actually has similar specs to the RTL SDR, except it's multiplied by 4 channels. With the RF front end, there are a few options there. So you can start from pretty much just individual mixers and amplifiers and filters and all that sort of thing in order to do the down conversion down to baseband. And in order to do that, you have to put a fair bit of thought into making sure that you've matched the components fairly well together and so on. And there's actually a bit more scope for things to go wrong as well when you combine it all onto a PCB. There's nothing quite like just going for a single tuner solution. It takes care of a whole bunch of different things, and so that was what ended up happening for this project. Now, this is where I initially started. You can see here that you've got a transmit path and a receive path, 2 channels, and initially there was also the idea of having a processor on board that had a fair bit of power so that it could actually do the protocol decoding in software on board, and that would be useful if, for example, the SDR was put into a rocket for telemetry, because at least high-powered rocketry, Monash high-powered rocketry, we tend to use modems for telemetry that have just a UART interface which goes into the rest of the electronics on board. So yeah, having the ability to do a bit of protocol decoding on board was something that seemed like it would be useful. In the end though, actually decided against that. The architecture definitely evolved over time. This is what was in the project proposal, so you can see the ARM processor is gone. It's just this FX2LP chip, which is mostly used as a bridge to get raw ADC samples over onto a PC. You can see here that there's an ADC which has been selected. Wouldn't recommend using this one. It got replaced in the final design. So in the final design, it's 1 ADC per, or 2 ADCs per channel, 1 ADC per obviously the I output and the Q output. So you've got a complex signal that comes out the back of the tuner. Down here, again, this is the FX2LP. It's pretty much doing all of the heavy lifting in terms of getting those samples off. So these ADCs are a serial device, and the samples get clocked out serially at about 48 megahertz. So you can't quite use an Arduino anymore, unfortunately. one thing about the tuner chip that I did choose is that the Myrix MSI 001 is pretty much not heard of. The data sheet for it is about 25 pages long, so you're in the dark for most of it. There's no reference design provided or anything like that, so there's a bit of reverse engineering that happened with some drivers that were available just on the internet, and well, the data sheet was a decent starting point as well. And then I found some photos online of a TV tuner dongle that happened to use this chip, and you could sort of like trace out where all the traces were going and what was connected to what, and just compare it against the tiny little data sheet and make sense of a few things. I'll talk a little bit about the choice of ADC, just in case anyone wants to go out there and build their own. It might be useful to know what the market looks like at the moment. So you're not actually going to find something that has 8 channels in the one ADC and simultaneous sampling on every single channel, and with 3 million samples per second or somewhere around there, which is what I was aiming for. The reason for that particular number is because the bandwidth of most of the telemetry signals that this SDR was originally intended to see from was about 500 kilohertz max, and just to go a little bit higher I felt was probably a good thing, but then not so high on the other end that you have to go for really expensive hardware for the digital data path. As you can see here on this list, that was sort of a first blush choice, and it doesn't quite cover this list of goodies. So what the solution is actually to go for a whole bunch of smaller ADCs rather than trying to find one package that has exactly what you want. There's actually a lot of 2-channel ADCs that are quite quick out there, and they're used for exactly this sort of purpose, RF baseband sampling. In the end, I ended up going for the Max 19777. This was the original test setup. This was before I got my hands on any ADCs. Circled here, you can see the FX2 LP. That's a development board for it. Just underneath it, we've got an FPGA. The FPGA just had a program running on it to simulate an ADC, and it had some simulated ADC samples, just in the form of a counter, which would count up, so you could tell that you're receiving data okay when you get a signal coming in that just looks like a sawtooth wave. Now, I chose the FX2LP because I'd come across it in a logic analyzer. It's a sort of a cheap logic analyzer that you can get off eBay, but it uses it at its core, and the idea is that it uses this GPIF bus on the FX2LP to do a whole lot of high-speed digital sampling. This is in the so-called logic analyzer. It's just reading in a bunch of logic states on the bank of pins associated with this GPIF. It can pretty much saturate a USB 2 bus, and so that's why that was chosen, because that data rate fits in pretty much spot on with having 8 channels, that 3 million samples a second, and then 12 bits per sample as well. And since the logic analyzer that I'm talking about there, the SIGROC, happens to be open source, it's a pretty good starting point as well for getting all the firmware and all the software up and running. And this is the final circuit design that I came up with for using this tuner chip. Bunch of sources for reverse engineering it. Things like the values for the decoupling capacitors sort of guessed, had a look around at some other RF devices that operate in similar bands, and sort of got inspired by them to figure out those values. Now, this PLL loop filter down here is in a similar vein, taken from a reference design for a analog device's frequency generator. That particular frequency generator goes up to about, I think, 4 gigahertz, which was a similar number to this sort of internal frequency synthesizer inside the MSI 001. So I figured that we'd be looking at a similar sort of design for its loop filter, because there's nothing in the data sheet for the MSI about what to do for the PLL. And that was actually a good guess. It seems to work pretty well. Over here, the input matching network. There's no need for valence or anything like that. Turns out you can do a single-ended input according to the data sheet for the MSI. There are a few things to take into account with signal integrity, because you don't want your clock to be creating a whole lot of noise, because that is going to get picked up very, very easily in the RF front end. So I think the main thing that has saved me there is the use of the 4-layer board. Just the fact that the signal traces are only about 0.1 of a millimeter away from a ground plane right underneath them, and that the ground plane is not interrupted, it just makes the transmission lines work really, really nicely. Get pretty much no radiation off them. You can see here in the picture there's a bodged in crystal oscillator. Sorry, not a crystal oscillator, just a crystal. That's running the FX2LP. Originally it was meant to run off the same clock as the tuners do. Now the clock buffer there, I don't know 100% sure, I'm not 100% sure if that is necessary, but it does make splitting up the clock to each tuner very, very easy. It's just TCXO goes into the buffer and then 4 lines out, 1 to each tuner, and that means that termination is really easy. There's some termination resistors on the clock buffer side, stops the signals bouncing back a second time. Oh, yep, and a separate power rail for digital and analog as well, and just the usual with the decoupling caps. Obviously, smaller values for things that generate sharp edges, as well as bulk decoupling separately. So at least for the current state of the project, the hardware looks pretty good. Everything on there is functional. There could be some room in there in the future for improving the RF matching network for the tuners. At the moment, it's just a resistive divider, and there's a lot of loss because of that, although it does have a good phase frequency response, very flat. On the software side, well, the firmware is done. That is fully functional. It's pretty simple. It's a bridge that sends commands back to the tuners from the computer, and then you've got the samples going the other way from the ADCs to the PC. But what's not finished really is the software that runs on the host PC. At the moment, just a command line utility that can dump out into raw binary files. In future, you'd probably want to integrate that with, GNU Radio or MATLAB. So here we've got the SDR. I've just plugged it in just now, and you can see over here that it's been recognized by Linux, or at least the Cypress chip there has. Now, at this point, there's no firmware running on the Cypress chip. Over here, we've got an EEPROM, which you can program the firmware to if you want it to remember your firmware and load it up at startup. But at the moment, the easiest way to do it is just to come over here to the command line, and we can upload the firmware like so, and you'll see that it's now re-enumerated the USB device, and we can tell that the firmware is running because it's got a little sketch on there that blinks an LED. Here I've got a bit of an antenna hooked up, and we're going to try and receive some FM signals. I've got a little program here which will read the data and dump it out into a raw binary file at the moment, so there's no real-time reading, unfortunately. And that's just tuned it into a frequency, and it's just sitting there dumping data into a file. Then we can come over here into MATLAB, and it's going to open up that file and plot it, or at least the frequency components in there. Oh yeah. Although I say the hardware is functional, it would be good to characterize its performance properly. Just because everything is working doesn't give you an idea of how well. Just a few small issues with the PCB. Other than that, I was pretty happy. There's about one bodged in crystal, and there's one bodge wire there for a line on the FX2, which was meant to be pulled high in order for it to boot, which wasn't. GitHub link down there if anyone's interested in the source code or the PCB designs. Yeah.